I wanted to mention, if anybody's got on D2 or MML yet, have y'all had any issues? Any issues with MML? Okay. I forgot to mention, well, maybe it's at the bottom. Okay. So at the bottom of each section, or unit rather, so we have our homework, then our quiz, and then our exam review that's not graded. But underneath that is all the multimedia from each section. So like if you go here, you'll see some interactive examples, a video lecture. It's just really all the media that your textbook provides for that section. That way you don't have to go hunting for it if you need it. So that's just underneath your homework. There's nothing there to do. It's just videos to watch and such. So for your reference. Did y'all have any questions on the homework at this point? I know we haven't gotten too far.
I have one for method 2. I think I wrote this down wrong. But the position at t, time t, is equal to the position at time equals 0 plus the, oh, you got it right there. Is it v prime of x, d of x, or is it just?
It's v, because this is, as we'll see, the generic form. Yeah. It has the rate of change of this function.
Gotcha.
Yeah.
Thank you.
So yeah, this is we can view this here as s prime.
Right.
Yeah.
Gotcha.
Or I guess I should write x, but yeah.
Those little details.
Yeah. Davis.
Yeah, it's number, sorry, I have it open, number 9 on 6.1. I was able to get it, but it took me longer than I wanted to find the v-intercept, or the y-intercept.
Number 9.
Yeah.
Find the position and velocity of an object moving along a straight line, given the acceleration, initial velocity, and initial position. So we technically haven't done an example like this, so I suppose we could work through this one, and then maybe forego the one we have in our notes. Is that fair?
Sure.
It's all the same, really. It's still based on the same principle, how we obtained position from velocity. We had 2 methods. We can obtain acceleration the same way. Okay. I'm so sorry, I missed exactly what you were having issues with.
Well, finding the y-intercepts, I guess once you've integrated, finding the initial conditions.
Oh, okay. Finding the c. Okay. So velocity then. How are we computing velocity? Right, good, yeah, antiderivative of acceleration. So maybe we'll do this both ways. We can, this is our antiderivative method. And then we'll look at the fundamental theorem is still, again, based on the antiderivative, so. So just a straight antiderivative. We're not worrying about the bounds, the displacement, or that kind of thing at all. So what is the antiderivative of 2e to the negative t?
Negative 2e to the negative t.
Okay, good. Negative 2e to the negative t. Plus our constant of integration. So that's the velocity function we're dealing with. And then again, to find that c, we're using the initial condition. So we have v of 0, v of 0. And we know v of 0, it gives us -2. So that gives us our single equation, single unknown. Let's solve for that. So we did mention, or I did mention last time, the initial conditions aren't always the constant. So a perfect example is when you have exponential functions. Because plugging a 0 in here doesn't just zero that out, and we don't just get c equals -2. With polynomials, that's true, however. Okay, so what we end up with here, v of 0, we've got -2 plus c is equal to -2. So c is equal to -4. No. Sorry, it's been a long day already. C is equal to 0. And then we plug that back in to our original velocity function. So therefore, velocity function is just -2 e to the -t. Yeah? And we needed velocity before we find position. So in order to find the position function, we'll do the same thing. We'll find the antiderivative of this, impose the initial condition, solve for c, and then we have our s of t function. Any questions on that? So let's do this same problem using the fundamental theorem method. We call that fundamental theorem of calculus method. But this time, just going to go back to this. When we listed this, we listed it in a very specific manner for the position function itself. So if we're trying to find v of t, then it's equal to v of 0, integral from 0 to t of what? dt.
V prime, so.
Yeah, v prime, which is what? Acceleration, yeah. So that's the pattern that fits here. We'll see a more generic statement of this here later on in our notes. But that's the pattern it follows. So v of t, v of 0 was the integral from 0 to t of our acceleration function, which was -2 e to the -t. Is everybody cool with why we're using a dummy variable here? Do we need to clarify that?
I could use clarity.
All right. So it's a dummy variable because the bounds we're using for x going from 0 to t. So when we find this function, it's going to be an antiderivative in terms of x, but then we're plugging these bounds in, which forces it as to turn into a function of t. So if we use t here already, then we would have, sorry, that's not, let me just make sure I wrote that down. Okay, my bad. Acceleration function. So if we were to write this in terms of t, then our antiderivative would come out to be another expression involving t, evaluating again from 0 to t, and we'll plug this in for this. I guess in this instance, it's kind of the same thing. You plug t in for t, but it's it's, I don't know, it's misleading in the sense of what this actually represents. So, I don't know, it's difficult to kind of keep that. I know usually sometimes I'll mix that up myself. It's not an egregious error, but, you know, it's technically incorrect. Okay. All right, so let's repeat this. Everybody cool with that setup right there? Does that make sense? All right. I wanted to do this just to remind ourselves where that input actually goes. We're given v of 0. Was that -2? We already found this antiderivative. So see, our initial condition's already built into that. We don't have to solve for it. Is essentially the difference there. So there's f of upper limit, antiderivative at the upper limit, minus the antiderivative at the lower limit. So I don't know, it's probably a toss-up as to which method is preferred for y'all.
On an example, you ask us to use a specific method.
I may or may not ask you to use a specific method. I don't know at this point. Perhaps with the problem with velocity, position, acceleration, no, but if you've seen some other examples in the remainder of the section, yeah, maybe then. Just as for like a net change in general. So then we end up with the same thing. This is -2, this is +2, -2 e to the -t. So we get for v of t. So different method, same result. Questions on that? So do y'all have a preferred method? Does one look easier than the other? Just curious. Yeah. All right. Okay, so we've got our velocity function. Let's go ahead and find the position. Which method do you want to use?
We should probably use the bottom one just because it's...
This one?
Yeah.
Again? Okay. All right, then, according to that method, we're finding S of t. So S of t equals what? Anybody?
S of 0.
Okay, 3, the initial condition, S of 0 plus integral 0 to t. Right, velocity, right. Yeah. 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 So velocity S prime goes here. Yeah, also a nitpicky thing is the dx attached to the antiderivative. I've just seen a lot of people in the past not put that. Again, so it's a technical thing. Remember when we established this early on in chapter 5? This dx represents what? Just in a mathematical sense. Yeah. Right. The rectangle width, right? So this was, in order to calculate the area, we had to measure the height of the rectangle given by the function and the width of the rectangle. So more generically, this dx represents, for us, it tells us that we're integrating with respect to. If any of you are going on to Calc 3, you integrate with respect to x, y, and z at the same time. So you've really got to keep that stuff straight. It does totally matter what variable you're integrating with respect to, just like it mattered what you were differentiating with respect to. So it's a really small thing, but please try not to negate that or drop it. Especially also when we start doing like trig substitutions, it becomes important. Integration by parts, it's important to account for those things as well. So don't develop the habit of just ignoring it right out the gate. All right, so we've got our 3 plus antiderivative of this thing here. Say that again, sorry.
2e to the negative x.
2e to the negative x. Do y'all agree? Yeah. Okay. Evaluated from 0 to t. So we'll take that 2 out. So that's e to the negative t minus e to the negative 0. And so we have 3 plus 2e to the negative t minus 2, which is 2e to the negative t plus s of t. Questions on that? Any other homework questions? I guess this example is similar to what we've just done, except for here, instead of starting with acceleration, giving a velocity function and then a position function, we're just starting off with the velocity and asked to give the position function using both methods. So is it all right if we bypass that, since we kind of just did that with another function? Is everybody all right with that? Again, a very similar problem here. Number 8. Let me go back. So here's our, the specifics that we've been working on here in the left column. The more generic ones are here for any general problem. We've got our net change, which was equivalent to our displacement, right? The net area under the curve gave us displacement, net change. And then future value, where we have just any quantity, the initial quantity, and the antiderivative of the rate of change of that quantity. So when we look at a problem like this, where we're just talking about Now, maybe population growth or what have you, whatever rate of change we're measuring, we can get back to the original population function, whatever the original function is. So we've got P prime of t, the growth rate of the population, and we're given an initial condition on that. At t equals 0, the population was 250 people. So our initial condition is this. So notice your homework question is, there's a couple that are similar to this. Notice it says, what's the population after 20 years? And then it says, find the population function for any time. Honestly, it doesn't matter what order you do this in. I think perhaps for most of us, it makes more sense just to find the population function first and then plug the 20 into it, right? But it honestly doesn't matter which one you do first. So population after 20 years, P of 20, what would that look like? What would the formula be for that?
Plus the integral from 0 to 20.
Of, we flip back one page?
30.
Yeah, P prime, great. So again, the generic formula that we're looking at here is we're after the population, so we want the initial population and the antiderivative of its growth rate. Here we don't need a dummy variable here because we don't have a variable in the upper bound. Just for clarity again, I'm going to erase, just so we can, for the visual people, that's our input right there. Remember also that the initial time is matching the lower bound of our antiderivative. So either way you slice it here with part A or part B, you're doing that first. Still, really the bulk of the problem is finding the antiderivative, right? So we've got our 250 plus, what's the antiderivative here? T plus, we'll leave, I don't know if you all like to leave the constants out or put them in. We'll leave it out. T plus. So antiderivative of 1 was t. What's the antiderivative of root t? 2/3 t to the 3/2, right? Do y'all have any questions on what we've done there? Okay, well this 0 is going to make all of this 0. I'm just going to assume that we're all okay evaluating this, multiplying it by 30 and adding it to 250. So 2638.85. Is our result. And so what does that mean?
Yeah, population.
Right, good. Population after 20 years. I mean, we'd probably say it's 2,638 people, right? That's what we have. Okay. So for part B then, it's pretty much the same except for we're finding P of t instead of P of 20. So we can see what changes there. So we already have that antiderivative. It's 250. Y'all all right with that?
Would you round it to a whole number
Which one?
when you have the 2,638.85 people, because you can't have 0.85 on the person?
Yeah. So it'd probably be more reasonable to say, the question didn't say like round to any decimal places, but that's a more realistic interpretation of that number. Yeah. Yes.
For part A, why is the second part of it, why is it still a T? Shouldn't it be an X?
Where?
Second
Part A?
Or- It's all in T, right?
Here
Yeah.
and here.
Let's use it.
No, we don't need the x here because we don't have any other variables up here. Yeah, so it's fine. If you did use x though, you would still get the same numerical. Yeah. But here it needs to be more consistent because we are finding p of t. We wouldn't want x in after we're done and say p of t is equal to all of this stuff in terms of x. Yeah. Any other questions? We'll just simplify this out to see what kind of function of t. So we've got, or x rather. So these bounds came from the dx, which means they're x equals 2 and x equals 2. So we have t in for x. And then 0 in for x just makes all of that 0. So then we distribute that out. We've got our 30t. We've got, what is that, 6, 20 t to the 3/2 as the population function for any time. And if you wanted to verify what we've done in part A, just plug in 20 for this t, see if you get 2,600, whatever it was. So honestly, if it makes more sense to you, just skip part B first, do that, and then find P of 20 just by plugging it into this. There's really nothing wrong with doing that. Just figured at least with this way we could show, using that particular formula, but we could go either or. Are there any questions on this? Okay then, so we'll start 6.2 if there aren't any further questions. We'll just have to see how this goes. I wasn't intending on covering everything in our packet. Technically, if you've come into this class, last semester in Calc 1, this section was taught. So I understand that might not pertain to everyone. So we'll just try to get everyone up to speed with what we're doing in 6.2 before we move on. Because honestly, the way we think about things in 6.2 really plays a huge role in 6.3 and in 6.4. We did kind of allude to this when we looked at Riemann sums. Initially, anyways, we were always trying to find an area bound by some function and the x-axis. And then that's where our rectangles came in. So here's the height of each rectangle. And there's the width of each rectangle. So we have all of these individual areas that we added up, gave us an approximation of the area, and then we said, well, to make an exact area, I need to let the number of rectangles go to infinity so I can fill that region up. So the number of rectangles going to infinity versus their widths going to 0, it's the same thing. However you choose to label that, it's really the same thing. So if I said limit as the number of rectangles goes to infinity, on this thing, it's the same computation. So maybe you vaguely remember that, maybe you don't, but that's kind of where we started off. And then we really didn't do much with that afterwards until this section. So in this section, we really look at what happens if I've got a function like f of x here and maybe g of x here. From A to B. Let's just say B is right there. So I want to know what's the area bound by these two curves instead of just the one curve and the x-axis. The idea is identical. We're just going to fill this region up with a bunch of rectangles. That's the slice and sum method. Sometimes they refer to that. You just slice it up, sum all of those things up. Let's look at this rectangle here. Rectangle that we're looking at here has a width in the x direction. So we think about that as dx, some small infinitesimal measure in the direction of x. So really this integral formula here, the width of each rectangle, that piece stays the same. However, the way we measure the height of each rectangle is different. So how would we measure the height of this rectangle? Sorry.
That's minus g of x.
Yeah, so the height of this rectangle, we're just measuring that linear dimension. So it's just this minus this, top minus bottom. Right, so if we knew specifically that was a y value of 10 and this was a y value of 5, we know instantly that that's a distance of 5, or that rectangle has a height of 5, right? But all of the heights of these rectangles vary. Really the only thing that we're modifying here is that this area bounded by these two curves from A to B, we still have this thickness or width, if you will. But now just the height of each rectangle is modified to f of x minus g of x. this instance, the height is measured by the top minus the bottom. This stuff does come back again, like I said, in 6.3 and 6.4. So we start looking at volumes, where we have to look at area, cross-sectional areas, and it matters how we orient these things, top minus bottom, versus a scenario. Maybe we have like two functions of y. Let's call this h of y, and this one w of y. And say that's a y value of c to a y value of d. So things change here, but if you just imagine that first scenario, if we take that first scenario, f of x and g of x, and just rotate it, it's the same kind of setup and interpretation. Except for we're no longer slicing the region this way, we're slicing the region this way. So each individual rectangle would come through here like this. So now that rectangle, or all rectangles there, they now have a thickness in the y direction. That's super crucial, I think. Maybe you have, once you see 6.3 and 6.4, maybe you've got a different way to think about it. But in 6.3 and in 6.4, it's super crucial to kind of draw these pictures and know what your setup is, because this involves an integral in terms of y. This is an integral in terms of x. So your bounds change, what you have to solve for in terms of your function changes. So it's super crucial. But the idea is still the same. Area, c to d, dy. How would we measure the height of that rectangle? Yeah, so let's say something specific. Let's say that we're 7 and this were an x value of 3. How tall is that rectangle? 4. How do we get 4? 7 minus 3. So generically we're saying it's right minus left. Or in this sense, it's w of y minus h of y. So I think if we can, be okay with how we set these things up, then when we start taking a region like this and revolving it around the y-axis, or if we revolve it around the x-axis to be able to set that kind of thing up, it's pretty much identical. Yeah, there's some extra things involved, but when we interpret this as far as its setup goes, it's virtually identical in the next sections. Yeah.
Because we're doing it in relation to y, would you still use d and c as your integral? Or should you use that's on the x-axis?
I'm sorry, say that again.
I'm sorry, so because you use d and c for, no, never mind, I got it.
Okay.
I'm good.
All right. Yeah, it's just they may not be the same values as we had labeled as a and b, so that's really it. If you want to put a and b there, it's fine, as long as you know that's a bound on y. Yeah.
So the basic idea is if the bounds are on the y-axis, make sure your equations are in terms of y. If it's on the x-axis, make sure your equations are in terms of x.
So is it essentially if your bounds are on the y-axis, make sure it's in terms of y? If your bounds are on the x-axis, make sure it's in terms of x? What do y'all think? Is that accurate? Yeah, I mean, if you're going to integrate with respect to y, your bounds better be in terms of y. If you're going to integrate with respect to x, they better be in terms of x. I guess more specifically, it kind of depends on the functions you're dealing with. You'll remember in Calc 1 where sometimes a function, it wasn't possible to solve for y, or wasn't possible to solve for x. So one of these scenarios in a certain instance might make more sense than the other. You might say, well, the functions were given to me in terms of y, but I can't solve for x. So I would just leave everything like that, for instance. So just having two different ways to look at it, depending on the scenario, one's typically more advantageous than the other one is. That's pretty much it. As we'll see, let me just show you a couple of figures. So, this example, where we're finding the area of this region versus example 3. So example 3 is a perfect candidate because we've got functions of y given to us. And if we're like, if we're thinking, I don't like y's because I'm used to dealing with x, then it's kind of a problem. Because if we say x is equal to y cubed minus 4y, how are you going to solve for y? You basically have to solve a cubic equation, right? So we have to try to factor that. So we can't really factor it because this x is x, right? I mean, there's a formula for solving a cubic equation like there's a formula for solving a quadratic equation. But if you've ever seen it, you would never want to use it. I promise you. It's ugly. Or like example 6, for instance. We might say, well, this one's like y equals x squared, but the other one's x equals to 2 sine squared y. I got to think about combining these two things together. Which ones do I want to integrate? X squared, not hard to integrate. Sine squared, is that hard to integrate? Harder than x squared, right? But if I were to solve this equation for y, like this one solved for y, then I have x over 2. I take the square root, and then I take the inverse sine of that so I can get y. Do I want to integrate that? Probably not. So this is another example where, seeing what it looks like the other way around, we might want to just stick with this is a function of y, so integrate this with respect to y. Is that clear? It really just depends on the situation. Okay. So example 1, we've got the curves y equals x cubed. So you can kind of highlight this. Y equals x cubed. And the quadratic is here. You just got to pay attention to the region it's telling you to find the area of. It's saying the area of the region between these two curves on the interval 0 to 1. So on the interval from 0 to 1, an x value of 1. So does everybody see the region of the area that we're looking for? It has to be bound by all of those things. Sometimes people are confused when it says find the region bound by this, 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 and this, and they see like a couple of regions. You've got to look at where all of those boundaries touch, where they form a particular closed off area or region. So we're finding the area of this object, whatever it is. Here's our x equals to 0, here's x equals to 1. Now, just because the functions are already solved for y, in general doesn't mean that that's always what you should default to. It's y equals to this function of x and this function of x, I should integrate with respect to x. That's not always clear cut. Here, hopefully it is. If we integrate with respect to x, our rectangles are top to bottom. And one of the things we're looking for is, does the top and bottom, top minus bottom function, do those ever change or switch places? So like, I start here with this rectangle, then this one, then I end over here with this one. Is the top and bottom functions ever change?
Yeah, no.
No, so we can take care of this with just one integral. The issue with, if we wanted to try it with respect to y, then our rectangles are running like this. And we have to do the right minus the left. This is a quadratic. Here we have to solve for x. This cubic we have to solve for x before we start working with the rectangles running this way. Does that make sense? So solving this quadratic for x is not difficult, and solving this for x is not difficult either. It's just it's really just a little bit more work if you want to do that. So I hope it's intuitive to use our rectangles running top to bottom. So what does our setup for this area look like then? Integral from 0 to 1, right? Because that was the interval we were given. To find the area bound by this and this between 0 and 1. So we go from 0 to 1. Top function minus the bottom. What was that? X squared minus x. So keep in mind we're subtracting off the bottom function, so you better have that negative to both of those terms. Everybody okay with the setup? Any questions? A lot of times in these problems, it's not obvious where your curves intersect. So in order to find the intersection of curves in general, how do we do that? Yeah, we set them equal to each other. And depending on the two curves, sometimes that's the hardest part of the problem, is to try to algebraically figure out where those two things are equal to one another. These two things are only equal to each other at 0, which is why we were given this other bound, because we would have never found this place. If we weren't told to stop here, we could just keep going, because they never intersect after that. But if we're finding the intersection points, which often we need to do, you have to equate these two. And we can come up with the same result as the graph tells us, but we got x cubed minus x squared plus x equals to 0. So those two are equal either when x is 0 or when this quadratic is 0. You can verify if you want to that this quadratic has no real roots. What's the fastest way to tell if a quadratic doesn't have any real roots, or if a quadratic doesn't factor in the sense of real numbers? Anybody remember? Do you remember the quadratic formula? part right here. That part right there is all you need to know about the quadratic, to whether or not it has real solutions or imaginary solutions. Because if this thing has imaginary solutions, then the b squared minus 4ac is going to come out to be a negative number. So we can just check here. Here's b is negative 1, so that's 1 minus 4 times 1 times 1. So we would end up taking the square root of negative 3 for this quadratic, so it has no real. Okay. So again, we would come up with only the intersection point at the origin. Yeah. And again, oftentimes that's a pretty difficult process to figure out where two things intersect. Any questions on this? So let me trace these out. Y equals to 8x. So again, we're looking for the region that all of those curves enclose. We're finding the area of that particular region. Maybe as you first start doing these, just choose, do I want to integrate with respect to x? If I do, then my rectangles need to run like this, top minus bottom. Do I want to integrate with respect to y? My rectangles run like this, and I have to do the right minus the left. So what would make more sense with respect to x or with respect to y? X or y?
Well, they're already set up.
So the functions are all y equals to a function of x. But again, that's not always the default. Just because they're already solved for doesn't make it easier. Really, if we're thinking about, okay, should we do it with respect to x, then I'm looking at all of the rectangles filling this region. Does the top minus bottom ever change? Yeah. So where does the top minus bottom change? Yeah. Right. So does everybody see that right here? Oops.
Is that right?
Yeah. What I see after this threshold, the rectangle's top and bottom change. So it's blue minus green, then it's red minus green. I mean, the graph isn't that great, so it's probably up to us to figure out where these things intersect so we know how to split this up. But that's the idea. With a region like this, we can still integrate with respect to x, but we do have to split it up.
Wouldn't you have to split it up if you integrate with respect to y as well?
Right, so what happens if we integrate with respect to y, then we have our rectangles doing this, from here to here, from here to here. Right, then it changes. Now it's red minus blue, red minus blue, red minus blue, all the way up.
So it's just extra work to switch.
Yeah,
around.
right. So if we integrate with respect to y, oops, sorry, that's our threshold where we have to change the bounds on y. But anyways, we would have to switch bounds and split this up into two different regions regardless of what variable we're using. Okay. It really doesn't matter how we proceed. We can set the integrals up first and then try to find their points of intersection, or we can find the points of intersection first and then set it all up. Do y'all have any preferences on how we should do that? Okay, so find the points of intersection first, and then we'll configure that area. Does that sound okay? All right. So here's kind of our preliminary work then. There's different intersections. We have 3 different intersections. The intersection of the blue and the green, the red and the blue, and the red and the green.
We have to like separate people individually.
Yeah, exactly.
Yay.
Yay. So where does, I guess it doesn't matter where we start. Where does 8x, I mean, maybe we can tell that that's the origin, maybe not.
Before we do that, should we change it in terms of like, is there y equals 8x? Should we change it in terms of x equals y? Because we're probably solving for y, right?
So if we change it so if it's y equals to 8 over x, this is already a function of x that we can integrate. So that is the y equals to. But if we want to integrate this with respect to y,
Right. That's what we
yeah, then it has to be, basically you're having a function solve for x right there. But you wouldn't see that.
Or are we not solving for y or something?
No, we chose to have our rectangles, my bad, I think I ended up erasing it. We chose to have our rectangles doing this.
Gotcha.
I mean, that looks like the origin, but it's whatever. What is 8x equal to x? When 7x is equal to 0 and x is equal to 0. So one and only one intersection of the blue and the green. This has an x value of 0. Since we're doing everything in terms of x, we don't really care what the y value is. But in order to get the y value, we just plug it back into either one of these. 8 times 0 is 0, or that's 0, whatever. All right, then we can find where the blue and the red intersect. So where does 8x equal to 8 over x squared? Okay. Yeah, so how are we solving that? All right, multiply both sides by x squared. 8x cubed equals 8, x cubed equals 1. Let's go over here. So x is equal to 1. So the red and the blue, these both intersect here. This x value is x equals to 1. So this x value here, where they intersect, is 1. And then we'll figure out where that equals to x, 8 over x squared. Method to solve. This time we get though x cubed equals to 8, which means x is equal to 2. So now we know this x value here is 2. And maybe you could have seen that from the graph. I don't know, the graph is pretty bad. You all right with that? So, all right. Now that we have the points of intersection, let's go ahead and set up the integrals that will give us the total certain net area there. Okay, so what's that going to look like? What's our first integral? All right, we go from 0 to an x value of 0 to an x value of 1. And what's the height of each rectangle? Yeah, 8x minus x. We're solely looking at this region right here. We're going from an x value of 0 to this x value of 1. Top minus bottom, 8x minus x. dx. What about the second region after the dashed line?
And the integral from 1 to 2.
Plus the integral from 1 to 2. Here we're going, picking back up at x equals 1, stopping at this point, which is an x value of 2. And then top minus bottom.
8 over x squared.
8 over x squared minus x. So that's going to generate the total area, the net area for that region. Do y'all have any questions? Just remember, when you find the antiderivative here, we're treating that as a power, so it's 8 times x to the negative 2. So the area is 6. Do y'all have any questions? I'm glad everybody made it safely. If you drove earlier today, you'd know it's pretty nutty. All right, if there aren't any questions, how about we'll take a break? Continue 6.2 when we get back. All right. Do y'all have any questions at this point?
Yeah, that's the translator.
No, this did not translate onto our meeting.
No?
We do.
Everybody's?
It's all right. And then I realized.
Maybe you'll have better luck making your own copies. Clearly, I can't function as a copier. All right. So we've got these curves in terms of y. The one on the left, I guess since you don't have this printout, just try your best. The notes online totally have this stuff. I don't know what happened. Somebody took the pages from the other paper. I don't know. We have to share a copier, so my bad. I didn't check. They usually don't have to. So this curve here is the y cubed minus 4y. g of y, we can call g of y x. Just like we call f of x y. And I don't have an orange, so this one will be our y cubed plus y squared plus 8. Okay, those curves don't intersect, but it does tell us to find the region bound by those two curves, y equals -2 and y equals to +2. I can't even see that. So here's y equals -2.
Isn't that approach to
Sorry, say that again.
the y approach to or is it quasi
H. So this one,
Yeah.
does it approach to or?
Is it approach to like
Oh, it kind of continues on this gradual path this way. So it doesn't have a horizontal asymptote. There, it's y equals to 2. So really, when you start seeing these problems here in 6.3 and 6.4, think about your rectangles. Which direction are your rectangles running? If just for instance, if I wanted my rectangles to run up and down, top to bottom, with respect to x, then I've got an issue here because I've got this curve in terms of y, and then this curve in terms of y. So if I want my rectangles like this, I have to solve both of those curves for x, which would be a very, very difficult thing to do. However, if my rectangles were running this way, now I'm thinking about right minus left. Right minus left. Does right minus left ever change through this region? No, so they're already in terms of y. The right minus the left doesn't change. So that's the easiest thing to do, because I don't want to solve those for x. So we should have everything in terms of y. Just over-exaggerate this rectangle a little bit, so we see that they all have this thickness in the y direction, which tells us that everything needs to be in terms of y, the function and the bounds. Yes?
So do we have to worry about sorry, the y cubed minus 4y equals x? The fact that some bounds are in the negative x, do we have to account for that at all?
No. So like even when we look at this rectangle here, let's say it's going over to negative x, right? So this region right here is in the negative x, but that doesn't matter because we're ignoring all of the things involving x. So we're not looking at it like this anymore. We're looking at it like this kind of thing. So we don't really have to involve ourselves with things like this.
I was just thinking, because it was left and y axis, is that,
So what about right here?
yeah. So because it technically, because you're rotating it this way, right, in this atmosphere.
Yeah.
So I basically, do the integration, it's just gonna give you the net area, so it's already gonna accommodate for that,
Right. It's going to totally get reconciled in that, yeah. Because all we care about, remember, is taking all of these rectangles, the length times the height, and the height, if you will, is measured just by the right curve minus the left. Okay, so what does the setup look like? The area is given by what?
Y cubed plus y squared plus 8 minus y cubed minus 4y dy.
Okay, remember we're subtracting off the left function, so subtract off the entire thing. And then we have all of this with respect to y. Everybody okay with that? planar-like terms, y cube's gone. We've got a y squared plus 4y plus 8. Integrating from -2 to 2. Y cubed over 3 plus 2y squared plus 8y, evaluated from -2 to 2. Comes out to be 112 over 3. Questions? Everybody okay? Yeah. Seem doable? Okay, here we don't have graphs, so sometimes that's the case. They just give you the function. There's no graph provided. So really, like I said, here, section 6.3 and 6.4, it's really beneficial to come up with a picture. All right, ln x. Let's just try our best here. So there's ln of x. Y equals to 0, which is the x-axis. We have all of this. X equals to 0, and y equals to 2. So again, we're looking at the region that's enclosed by all of those pieces. The region enclosed by all of those pieces is this region here. So we're looking at that particular figure. All right, so then the question is, do we want to integrate this with respect to x or with respect to y? Oh, it does say with respect to y. Okay, so what's the difficulty that arises then with integrating it with respect to x? You have to split it, and then we have to integrate the natural log. So right, so we would split here across this threshold. Finding this area, we don't even need an integral, do we? It's just what's the length times the height? It's a rectangle. But then when we get over here and say, all right, well here's one rectangle. The top is what? 2 minus the bottom, ln x. So then what we're looking at for this piece right here is the integral from that point to, what is that? Where the ln of x equals to 2. Right? Or e squared. That's really not the issue. The issue is this part right here. As we'll see later, integrating ln isn't an issue, but we don't know how to do that right now. I mean, maybe you know prior knowledge, but for most of us that's a problem. What function do we take the derivative of to get natural log? If that were 1 over x, like we could integrate that to the natural log, right? But so that's the problem with integrating that with respect to x. So just write this here with respect to x. This is actually our x value where the log crosses the axis. We would go from 1 to e squared on that function. Okay. So that's not a viable option at this point for us to utilize. Does everybody have that? If you want to write that down, does everybody have what they need for that? So it made it a little less convoluted for us by saying integrate with respect to y. If we're integrating with respect to y, do the right minus the left functions ever change? No, they don't change. However, this piece right here, y equals ln of x, and if our rectangles are running this way, then again their thickness is some measurement y, which that tells us that everything now needs to be in terms of y. So like I can't integrate with respect to y and have this ln of x in here. We just have to solve y equals ln of x for x. If y equals ln of x, then x equals to
E to the y.
yeah, e to the y. Okay. So that's our right. What's when we say right, the e to the y minus the left, what's the left? Yeah, it's this line right here given to us by x equals to 0. So it's e to the y. We'll go ahead and write this out minus 0 just so we can explicitly see that. But it's just e to the y that we're integrating. Remember the bounds also in terms of y. So the lower bound to the upper bound this way. So our lower bound is given to us, y equals to 0. And the upper bound is also given to us as y equals to 2. That one's e to the y evaluated from 0 to 2, which is e squared minus 1. And if we needed an approximate, we could just punch that in our calculators. So cross this out. Y'all have any questions on that? All right, I want you to all to try number 5. Both integration with respect to x, set that integral up, and then set another integral up that takes care of the area with respect to y. Sometimes you can use both.
I got
Well, I didn't get a chance to see everyone's completed result, but most of you had the right answer, which is good. But I'll go ahead and write them down for complete notes. 5/12. Yeah. 5 over 12.
I got myself out.
Okay, with respect to x, go ahead and draw our picture over again. We have our square root and cube root.
It's always been like your hands.
Okay, so in both cases, you've got to find their intersection point. This one is clearly the origin 0, 0. When does x cubed equal to the square root of x? Yeah, when x to the 6th equals to x, when x to the 6th minus x equals 0. So we factor out x to the 5th minus 1 times x equals 0. 0. When x is 0, got that one here. And when x to the 5th equals 1, then x equals 1. So this is, we can plug it back into either or. We've got an x value of 1. 1 cubed is 1. Square root of 1 is 1. So we get the y value as well. Since we're doing with both respects to x and y, we want the both ordered pairs x and y. That makes sense?
Yeah.
Yeah? Okay. So here, this is preparing to integrate that. Let's write that as x to the 1/2. Top minus the bottom. So remember that you're going to add 1 to this power. So we have x to the 3/2. And then we divide by the same result. So x to the 3/2 divided by 3/2 is 2/3 x to the 3/2 minus x to the 4th over 4 from 0 to 1. So that's just 2/3 minus a 4th. 5/12. Still have any questions on that? Sorry, I wasn't able to fully get around and see everyone's. They weren't done. Okay, same region with respect to y. With respect to y. Let me do this way. With respect to y, now our rectangles run from right to left. So that's dy. Which now means you've got to solve both of those curves for x. So if this is square root of x, then that's y squared equals x. Y equals x cubed, and that means x equals the cube root of y. So our area, 0 to 1. Right minus left, so we have cube root of y, rather y to the 1/3 minus y squared dy. And that's 5/12 as well. So rightfully so, we're not revolving this thing around any axes or anything like that. The area of that region is the area of that region, whether we look at it like this or like this, right? So are there any questions on either one of those? Okay. Did this one print out?
Yeah.
Were you? Okay. Yay. So this is just a setup. The functions are kooky and the bounds are weird. So really, we want to first identify what's the most efficient method with respect to x or with respect to y. With respect to y. So if we're with respect to y, then our rectangles have to run this way. Hopefully, clearly from the graph, we can see that the right minus the left does change across this point right here. But I think earlier we alluded to why this is easier in terms of y. Because we don't want to solve 2 sine squared y for x. Sorry, 2 sine squared y equals to x. We don't want to solve that for y and have it in terms of x dx, right? So dy most efficient with respect to y. So let's label our points here. Origin 0, 0. This first point of intersection is the 0.84, comma 0.71. And the next point, 1.46, 2.12. All right. So the first region, this bottom region, what does the setup for that look like? Integral from 0 to 0.71.
And then it would be the square root of y minus 2 sine squared y.
Try to do that in blue. Do y'all agree with that? With the first region? Again, since it's in terms of y, we've got at y equals x squared, we have to solve that for x. And then our second region, we go back, we pick back up at 0.71. Yeah, it's 2.12. And then just the right minus the left have switched here in this region. So now we have the 2 sine squared y minus root y. dy. So there's our setup. Do you have any questions on that? Okay, so setup only. This one's a setup as well. So we wanna this is black. Yeah, we'll just do this one in black here. All right, so that one's our sine 2x. And we'll do the other one. So for question 7, what's the most efficient with respect to x or y? With respect to x, do you all agree? So our rectangles in here, top minus bottom. Do we want to set the integrals up first and find the intersection points, or do that last?
Points first.
Points first.
So you don't want to keep going just under one also.
Yeah,
Under 1/2.
yeah, so all we've got is this graph, so we'll just say the area bound by these two regions.
You just left right infinity one more.
So points of intersection. Points of intersection where sine 2x equals sine of x.
X equals 0.
When x equals to 0, that'll give us this point here,
2 pi. Pi, my bad.
pi, and somewhere there, right? So what's the trick here to solve this? Anybody have any ideas? Not fractions. Do we know an identity for sine of 2 theta times sine of 2x? Yeah. That one.
2 sine x cosine x?
Yeah, that's what we're looking for. 2 sine x cosine x. That way we've got two terms both involving a sine. We can just factor that sine out of both of those terms. So you've got 2 sine x cosine x minus sine x equals to 0. Factor out our sine. Leaves us with 2 cosine x minus 1 times sine x equals to 0. Now we've got two things that equal to 0 we can solve for. Here, I'll move that up for you. Okay, so when does sine x equal 0? 0 pi. Do we need to keep going? 2 pi. But this is pi right here. That's x equals to pi. Oops. So we don't need to really, keep going after this. When does 2 cosine x minus 1 equal 0? When does cosine x equal half? Pi over 3. Same, just a radian versus degree. Where else? 2 pi over 3, cosine's negative at 2 pi over 3.
Right.
Back over here.
5 minus pi.
Yeah, minus pi over 3, 5 pi over 3. That's past pi. Don't need it. So points of intersection are x equals to 0, pi, and pi over 3. So we knew that one. X equals to 0. Now we have this one at pi over 3. So we have sine 2 minus 2. All right. Do you have any questions on that? Okay. So then our area. First we go from 0 to pi over 3. Top minus the bottom. Second region, go from pi over 3 to pi. And then the top and bottom switch to sine minus sine 2x. So there's our setup for that area, the particular region. y'all have any questions on this? Yes.
So I think I'm not sure adding like from respect to y to respect to x, or is it always like just
For us, typically no, because you're always given a function like in terms of x or y. So we have the ability to solve for either x or y. Like if maybe one of them was easy to solve for y, you could take like, if we had two regions, like this region and this region, you could do with respect to x and then with respect to y, because as we saw with that one example, they'll produce the same area regardless. So for us, no, there's never an instance that I've seen where that's relevant, but you could certainly do that. Any other questions? Let me just, here's your, well, I'm not going to continue that. We already finished it. Here's our recap, and I'm gonna add to this some things you need or might need to remember for getting through this homework. A couple we've already seen, so let's just say 6.2 homework. Seen this one. The other one is doubling for cosine. Remember, this one had 3 representations for that. It was cosine squared minus sine squared. That's kind of the main one. The other 2 are result in using a Pythagorean identity on either cosine squared or sine squared. So the other 2 cosine squared x minus 1. That's writing sine squared as cosine squared minus 1, combining these terms. And then we've got 1 minus 2 sine squared x. That comes from writing cosine as 1 minus sine squared and combining like terms up here. The other 2 things you need to remember is how to integrate sine squared and cosine squared. But those are handled with another identity. So integrating sine squared, you're going to write sine squared as 1/2 times 1 minus cosine 2x, and cosine squared as 1/2 times 1 plus cosine 2x. You need to remember those. They don't go away. Maybe by the time we get to series and stuff, we'll really integrate a lot of that. But even certain tests when we're dealing with series involves integration. So
These aren't the antiderivatives of sine squared.
right, these are not the antiderivatives. If you have the antiderivative of either sine squared or cosine squared, you rewrite them like this, and we find the antiderivative of this right-hand side here instead. So you'll need those for your homework. Questions on 6.2 before we move to 6.3? If you think of stuff in the next class, please ask too. I know a lot of times it's hard to, you don't know what you don't know, right? All those, the known unknowns and unknown knowns kind of stuff. So if you think of something, just please ask. We need to at least start 6.3 today. So here's what we're starting here is looking at, we're starting to look at volumes. How can we compute a volume with an integral? So when we're looking at the general slicing method, starting off 6.3. The disk washer method also at 6.3, and the shell method at 6.4. So these are all volumes that are generated. start with the general slicing method because how we obtain a volume with this method plays right into the disc and shell method, or the washer and the shell method. So we've got three kind of regular geometric figures. The idea of how we find the volume for these is directly related to how we would find a volume for a piece of bread. So maybe let's start off with this one. Maybe everybody remembers. How do we find the volume of this rectangular prism? Yeah. But let's look at it in a slightly different way. The face here, if we can't tell, the face here is a square. So let's call this, I don't know, W and W. Yeah, W squared times whatever we want to call this dimension here. I heard L, so we'll call that L. So that's the volume. But notice what's allowing us to do that is, or a way to look at it anyways, is you've got this square sort of, scooted along this length L. So we have this square, this square, this square, this square, this square, all of those squares that many times. So then what would the volume of this cylinder here, right circular cylinder be? Close. Yeah. So we look again, the figure that's common to this all the way through is the circle. So what's the area of the circle? Pi r squared. And we're just extending that up right here. We'll, I don't know, call that H. So this volume, pi r squared times the height. What about our little triangle ramp thingy here? Yeah, right. Shape that's common to that triangle. So we find the area of that. 1/2 base times height. We just extend it out, whatever we want to call this. Let's call it L again. So the volume, 1/2 base times height times L. I'm not going to try to draw the bread, but that's kind of the idea. What we're looking at here is really plain to us because they're all regular shapes. But just imagine slicing into this ramp this way. Every time you slice it, if we could take that little thin piece out, it would be a right triangle. Slicing through this cylinder, we would always get a circle. Slicing through this stick of butter, we would always get a square. So we want to translate that, or what we're going to translate that into is we want to look at the area of the cross-sectional slices. Of course, in something like this, a cross-sectional slice isn't a regular geometric figure, so we can't just say, oh, the area of that is length times width, or whatever it is. They're typically described by a function instead of, a figure. So here's the general slicing method. If we want to find the volume of this right here, it's maybe not as elaborate as a piece of bread, but the idea is we just slice through here and look at each cross section. So here's a cross section. We compute the area of that cross section. All cross sections are the same shape. They just vary in height. They could vary in width or whatever the case may be. But that's the idea, the area of each cross section, and then we sum all of those up, allowing the number of slices or cross sections we put in there to go to infinity. Again, if we think about slicing into this though, it's still a rectangular thing that we're doing, right? If we slice into this with a knife, it's still generating a really, really thin rectangle. But then when we look at it, when we sort of rotate this picture, we see, well, it's not really a rectangle though, it's an arch. The cross-section is now an arch because we're not dealing with a two-dimensional figure anymore. It's a three-dimensional figure. But find the area of this thing, and then we say, well, this is how thick it is. So we take area times thickness, we have the volume of that cross-sectional piece. And then we just add all of those up. So that's where this formula is coming from. If we take the area times dx times the thickness, you have a volume. And remember, the integral is just an infinite sum. And we're summing up all of those volumes. Let's say that a of x is the area of each cross section. So cross-sectional areas. When you're asked to find a volume, the heart of the problem is determining, well, what is that function that gives me the area of each cross-section? Everything else is just my starting point, my finish point, and dx, which is the thickness of each one. So when we look at general slicing, disc washers, and the shell method, we're all building upon this formula. The area function, a of x or a of y, whatever it is, those are the things that vary from problem to problem. So like if we went back to that first page, the cross-section was a right triangle, then it was a circle, then it was a square. Those are the things that vary. Yes?
It seems like a of x is extending into a different dimension than d of x. You have one extending in that direction and one this way, so I don't understand how they're both based on x.
So we're just going to take this picture. We're not going to think about the three-dimensional solid. All we're going to think about is, like in the xy plane, from here to here, what is this curve? So that'll generate this right here for me in a two-dimensional sense. And then I can say, okay, well, if I know my cross-sections are circles, then that's what's giving me the figure coming out this direction.
Okay, so you'll know kind of what your shape is.
Right, yeah,
Okay.
yeah. So these problems, we can back up to this formula, but these problems are as such, find the volume, circular base, whose cross-sections are equilateral triangles. So this is, if all of the cross-sections are equilateral triangles, then this is the volume that is generated by that. But we're not thinking of it in a three-dimensional sense. We're just going to think about it and work with it in a two-dimensional sense. I forgot what figure that is, sorry. Oh, here's the first. Pretty sure I had the figure for that. I don't know where it went. So something similar, anyways. You've got some sort of boundary, and then we're gonna slice it. The slices here are semicircles, and then we've got to imagine that just like our rectangles in 6-2, all of those cross sections are filling that region up. We're only able to visualize one of them at a time, but then we can, as we vary that, we can show that solid. We fill them up with half circles. We can see that that three-dimensional solid that's generated when we do that. But the way we want to think about it is we want to think about it in the XY sense only. The boundary curve is a circle, so we want to think about this way, and then the points of the apex of the triangle is coming out at us. We can't see it because we're looking down on it. Does that make sense? So yeah, just take this figure, take this thing and rotate it where this point is facing you. You don't see it. I mean, we see it once we do this right here. Now I'm seeing that triangle, but again, it's really coming out at you in this direction. I can't draw it, but it's this direction coming in. Yeah. So anyhow, we don't have to worry about the three-dimensional aspect of it. It's probably a long-winded way to say that. But, sorry, I at some point I owe you 3 minutes. So y'all have a good weekend.